Good morning, good afternoon, good evening, wherever you are on this planet.
Hi.
Sorry we're late.
We how many doctors of space does it take to start a live stream? Apparently at least two.
At least two,
At least
especially
two.
when it's raining in San Francisco and internet doesn't work and we have to find a new Wi-Fi, etc., etc. So my name is Franck Marchis. I'm a director of citizen science at the SETI Institute and the chief scientific officer of Unistellar. And with me have...
Hi, I am Sgro. I'm the exoplanet lead astronomer for Unistellar Citizen Science at the SETI Institute, and I do a lot of outreach, and it's great fun. Yes. Hi.
Among other things. Okay, so today we are going to briefly talk about some results, right?
Yes, we're going to talk about some results, what's coming up for 2025, and answer any of your questions. So if you have any questions that you want to ask live, please put them in the chat and we will get to the ones that we can during this live.
Exactly. All right, so for those who have no idea what we're going to talk about, we're going to talk about some scientific result that was obtained with the Unistellar network of telescopes. So you have two Unistellar telescopes behind us. There is the Odyssey, small one is the other way. We need coffee, obviously.
I would be a bad meteorologist.
This is the Odyssey, and this one here, like you, this is the Eviscope 2. Exactly. Okay. So with these telescopes, you can enjoy observing the dark sky and also do science with SETI Institute. Okay, let's talk about some results.
You ready for that? Yes, we're going to talk about some asteroids.
Yeah, I know. Asteroids, right? You love them.
Oh, yeah, they're just my favorite.
So asteroids are everywhere in our solar system. And we discovered in 1992 a new population of asteroids called the trans-Neptunian objects, which are beyond the orbit of Neptune. That's why they have this name. And astronomers have been observing, characterizing them over time. They're more and more interesting because they contain some information about the collisional past of our solar system. They can explain how planets were formed, for instance, especially the core of icy planet and gas giants. And it's been a very interesting journey to characterize them and to understand this population. Unfortunately, they're generally relatively small. We're talking about 1,000 kilometer max, 100 kilometer in average, and they're super far. So since they're small and far, and they reflect only the light of the sun, they're very difficult to be seen in direct imaging. So we're talking about, most of them are typically a magnitude of 20, 21, 22. So you need like 8-10 meter class telescope to see them.
And to give you an idea, the naked eye can usually only observe up to 6 magnitude stars, so quite dim.
So a lot of my colleagues spend hours and hours observing with large surveys those trans-Neptunian objects to characterize them, to refine the orbit. In beginning of last year, mid last year, Damia from the Observatoire de Paris contacted us because the project called Unistellar predicted an occultation of one of these trans-Neptunian objects called 2013 UL28.
Such a beautiful name, right? Yeah.
So 2013 UL28 was occulting a 12 magnitude star based on their predictions. There was some debate because another group made another prediction and it was slightly offset. But in any case, we decided to motivate our network to observe this. Mm-hmm. So when you observe that, what you do? You just take the telescope out, you press one button to go to the location of the star, you wait for the timing, and you press another button to record. And if you are on the path of the occultation, which is where the shadow is moving, you will see the star disappearing for half a second, 2, 3, 4 seconds, depending on the size of the asteroid.
Can actually show you an example of this. Yes. for this particular asteroid.
So Charles Sherrock from, I think it was in Maryland?
Yes, he is in Maryland.
In Maryland, observed this. Hi, Charles. I don't know if you're observing, if you're watching us now. And you will see this is the occulted star.
And, it's so fast.
This is accelerated by a factor of 5, if I remember, or 10. But
Play
You
one
see,
more time.
it's a very short disappearance. This one lasted like not even a second.
Yeah.
And so we have, in fact, multiple people in our group that observed this event. It was transatlantic event, so that means they could observe it in Europe at 3 a.m. or in United States at 9 p.m., 10 p.m.
Beginning of the night. Yeah.
Beginning of the night. So guess how many observations we got in Europe?
How many?
2.
Was it cloudy?
It was late at night.
yeah, it was cloudy and 3 in the morning.
Exactly.
So the detections of this particular asteroid actually came from the US and from Mexico, from Ivan Benzor.
Hi, Ivan. So Ivan observed it. Do you have the codes by chance?
I do.
So we're gonna show you the codes. What we call codes is basically the timing of disappearance based on the location of the people, and that's allow us to draw the shadow of the object. And look at this, how beautiful it is. So some of our observation, I know you don't like these figures, but
excuse you.
You should tell me no, I don't want to show that, it's ugly. So this is the code of Ivan. He was in Mexico, in northern state of Mexico, I forgot which one. And he was almost at the centrality of the longest one. And here we have the code of our other observer, Charles.
In Maryland.
And there is, I think there is another one that was observed by Ariel. You know who is Ariel? Ariel Gekowski. Have you heard of her?
Oh, our coworker.
Our
yes,
coworker.
the comet lead.
Yeah,
it's her birthday tomorrow, by the way.
It's tomorrow. We can't say happy birthday. It's tomorrow.
Okay,
Bad luck. Write to Ariel tomorrow. But she observed it too, but she used the Odyssey in the small conditions. So we don't have a code yet here, but maybe it will come.
Can I say something?
Yes, tell me.
I'm going to get fired. No, I'm just kidding. So just to kind of make it clear, when the asteroid is casting a shadow over the Earth, that's basically when you are in a different part of that shadow, essentially towards the edge or towards the center, like you were talking about, you're kind of sampling a different part of the asteroid. So that's why the occultation actually lasts for a different amount of time based on where you're at in the shadow, because you're sampling, say, a part of the asteroid's edge versus a part of its core. So that's essentially the shape that you're seeing here, right?
So this was generated by the Occult software. I think David Herold sent us this. The lead of this project is Joseph Anush. Thank you, Joseph. It's been a very difficult project to process because it's outside our normal scope of observation for occultation. The star is fainter than what we generally observe, so we have to use some smarter way to do the analysis. So it took a bit of time, but this happened when? January 30, and we have basically announced the result in February 5th. So it's not that
we're moving
much.
Along.
In the scale of the universe age, I mean, people can wait
blip.
6 days, right? All right. Thank you, Joseph, for all this work. And thank you for all our citizen astronomers who observe it, and also the other citizen astronomer from the IOTA who observed this event.
Yeah.
There is another one from the same object in the future. And now we know exactly where the asteroid. That's the reason we're doing all of this.
Exactly. And speaking of asteroids, there's something I think is really exciting, is the first kind of record-breaking thing for the Unistellar network as far as an occultation of a binary asteroid. Do you want to talk about that a little bit?
Yeah, that's my field of research. That's one of the
I can't win today. Gosh.
So
I was trying to set you up.
I know.
Just saying.
Okay, it's been a long morning already. So Sadeya, it's a man-belt asteroid. Michael Camilleri and David Herold mentioned that there is a binary. This is a suspected binary based on the fact that when you look at the light curve, you see two components, like if there was two objects rotating at different speed, basically, and you also see some. I don't think for this one they see it, but sometimes you see mutual events. We call that, when basically it's two components and one eclipses the other one, so there is a drop in magnitude. I forgot the detail for this one, but we knew it was a suspected binary. And Van Hoekman observed an occultation that we predicted for this asteroid on January 3rd of this year. And what did he see?
He saw something really cool. So Van, if you're watching, congrats. This is really, really neat. And I believe that Van is in Virginia, if I'm correct. So this is, again, another video like we just showed. But if you watch, you can tell that this is a binary because there are two blinks. I'm going to fast forward a little bit. All right, there we go. We just got to watch. It's very quick. We're still waiting. And there goes. Yep.
They blink twice.
You'll see that.
So when something blinks twice is because either the source is a binary, meaning the star is a binary, or the asteroid is a binary. But in this case, analysis show that this is coming from the asteroid. So we confirm with this observation that Sadeia is a binary asteroid. And Joseph submitted recently a CBATE that will be published hopefully very soon, maybe today, maybe tomorrow. And in this CBATE, he basically did a short analysis, a simple analysis. So the system as the primary occulted the star for 0.9 seconds. And the secondary that's secondary for 0.9 seconds, the primary for 4.2 seconds. But basically from that, we know now the size of the two components. We know that it's a 12 kilometer and I forgot, a 4 kilometer system. So there's a 12 kilometer asteroid and a 4 kilometer asteroid in orbit around it. Those systems are amazing because we learn a lot by studying them about the density of the asteroid. And frankly, this was a kind of a dream for us when we created this occultation program, is to be able to confirm binary asteroids. So it's done. Another achievement of the Citizen Science Project.
Yeah, it's pretty incredible. There's been a lot of firsts recently in this last year, and now just the beginning of 2025, again, this being the first binary asteroid occultation that was detected with the Unistellar network. So congrats, Van. And don't you have a triple asteroid system named after you?
No, I discovered a triple asteroid system.
Okay.
And I have an asteroid named after me, and I still don't know if it's a binary or not. So maybe we should organize a campaign to observe the asteroid Marchis.
Observe Franck in space, yes.
And maybe it will be a binary. That would be kind of cool.
That would be incredible. All right, so I know we started a little late. I just wanted to talk about a couple of things first. Really, really briefly, and I'm looking over here because I'm going to show y'all an image. So in the world of exoplanets, which you all know, I think by this point is my favorite thing.
While you're trying to find this, I will just say hi to people watching us from North Carolina, for Grand Prairie, Texas. That's not the way you say it probably, but I cannot Americanize Grand Prairie. So
that was good. That was it. That was it, yeah.
Pakistan. Hello, South California, Brazil, Germany, Iran, hello,
hi.
France, New Mexico,
hi,
Oklahoma, Washington, D.C. Thank you. We are talking about some results of the Citizen Science program from Unistellar and the SETI Institute. And now we're going to talk about your favorite topic.
Exoplanets, yes. So again, really briefly, because I wanted us to be able to get to questions. But we have been undertaking a new campaign. We're calling it Uptempo. These are essentially exoplanet, not quite candidates, but they are potential signals of exoplanets that were seen by NASA's TESS. So the Transiting Exoplanet Survey Satellite. Usually TESS observes certain portions of the sky for 27 days at a time, and it will occasionally see transit signatures where we see evidence of a planet dimming the light from its host star as it orbits around it. And typically, when TESS finds one of these signals, people follow it up, it becomes a candidate, and then we confirm it with other scientific measures. these up-tempo targets, we are working with another scientist at the SETI Institute. Doug Caldwell, yes. To basically look at some signals in the test data that didn't really get caught by anybody or flagged as candidates by the test pipeline. So we're just kind of taking it on ourselves to say, hey, could this actually be a planet? And we had something really interesting happen in November of last year and just recently in the middle of January. We had this one target, TIC 4374712.0. What? Sort of, isn't it great? Yes, beautiful.
Nice name,
but we observed it based off of what was seen in the test data before, to essentially say, hey, if it's a planet, it could be transiting now. And we saw some interesting signatures. So these are they're not for sure yet. They're not bona fide detections.
Well, you're not 100% certain of what you're gonna show. That's science, by the way. You don't have to be 100% certain.
Yes, ignore the TOI 999. It's just a placeholder. But this, just for instance, to kind of show you the process, is what we would call similar to an egress signature. So as the planet is finishing up crossing its star, this was caught by Wataru in Japan, and another observer actually caught a similar signature from Japan this past January. So we're seeing. This also happened in November, where we got a little bit of data at the transit's beginning, at the transit's ends, that could be indicative of a potential real transit signature. So we're following up on that now. And I just wanted to mention that because, for one, it's really cool. This is the scientific process. We see data, we try to back it up. If we don't have enough data, then we're going to keep observing it and essentially keep going until we get a non-detection or a detection. So we'll be observing this again February 23rd, visible to Japan and the US, and again in March if we have some time.
And Ryan wants to say hi. Ryan, our lead of satellites planetary defense, is listening to us. Hi, Ryan.
Hi, Ryan. Hi. I told him not to do this, and here he is.
Okay. Today's the day, huh?
Today's the day.
So we do the cool thing for the people who just catching this conversation is that with a small telescope now, you can discover exoplanets, confirmed exoplanet candidates coming from this.
Exactly.
And this could be a new exoplanet that TESS did not even yet has as a candidate, which is kind of cool.
Mm-hmm.
We have an idea of the size of this exoplanet?
No, we do from the original test data. I don't remember it off the top of my head because, again, all of that has to be confirmed with actual ground-based data and follow-up. So it would definitely be a gas giant, similar to a warm Jupiter type planet.
Good. All right. Well,
I got one more thing to show you before we go on to our questions.
Yeah, just want to remind people, you can find exoplanets. So it takes time through, it's like 3-4 hours of observation. But you don't have to babysit your telescope. It's fully automatic. So you put it on, you turn on the thing, you point to the right star, you press the button,
and you leave it,
and you can do something else.
This was actually a 16-hour window because it's a very long duration. So we had people, across from Japan to.
You have an uncertainty of 16 hours in the window.
It was a 16-hour window, so it's an 8-hour transit. So for ones like that is what we're really good for because we have people all over the world who are doing a great job observing and picking up when somebody else can no longer observe.
Good. All right, so you have something else to show us, something very cool and colorful.
Yeah, and then we're gonna answer your questions and stop talking. But ta-da! Thank you, Peter Picorni, working with our team for making this video that basically sums up all of the citizen science observations in 2024.
So 10,503 citizen science observations taken in 2024.
And over 11,000 if you count our new satellite mode. But this is the first time that we've surpassed 10,000 observations with the Unistellar network in the span of just a year. So this is a big deal.
Because that was the goal we had set last year. Last year we had a meeting and we basically, I don't know why we decided 10,000 because it was a good number, but also because I think it was reachable if we make some efforts. So we have reached this KPI.
Yeah.
So
And now, and you can also see how many, just the sheer number of observations that were made with each campaign. And of course, by the end of the year, transients took over the entire map. So that's our Cosmic Cataclysm program, people observing supernovae and the like. We had almost 6,000 observations in that program alone. So congratulations, y'all.
Yeah, and we should talk, next time we're gonna talk a bit more about this cosmic cataclysm and talk about some scientific results and how we're gonna do, and we're gonna expand it, because there's some of ideas with the new survey coming in. And yeah, congratulations everybody. This is a work of a community of 2,500 people connected on Slack, communicating with us, plus and also the effort of my fantastic team.
Great job, everyone.
Ryan is part of it, with Brian, Ariel,
and
Tom, Ian, and Stormy.
Yes, and Stormy the dog who's here.
And Peter and Joseph. I think I have everybody.
Yeah? I think you got everyone. Yes.
So thank you.
And I think we have a time for a little Q&A now. I know that Tateki Goto asked a really great question. If we can put that up across the screen. I think this one is for you, Frank. He specifically called you out on Slack. So this one is for you.
Oh, that's a very existential question.
The chicken or the egg? Which one came first?
Well, the story is that Arno had the idea of the telescope. Well, Arno Malvache, the founder of Unistellar. And when we met at CES, we talked about citizen science. And I mentioned that, I remember vividly mentioning that I think we'll be able to detect exoplanets with this thing. And everybody was kind of surprised, the other co-founder, Antonin and Laurent, but that was my bet. So what came first is definitely the telescope and the idea of making astronomy accessible. And I came into the story as the astronomer that provided a bit more value to this telescope, because I believe that it's great to observe and get pretty picture of a telescope. I mean, people love that, yes, but participating to improving the knowledge of humanity by doing telescope observation in your backyard has no price. So for me, Unistellar is the citizen science network of digital telescopes.
Very good. Oh yes, Mike, reach out to us on Slack, and we can send you some materials for outreach.
Can you ponder up the question? Can I get a copy of the 2024 observation to use in my? Yes, we are going to post it on our Slack, so you will be free to download it, and we'll be also on YouTube. Remind me to do that. I forgot again.
Yes.
And yeah, so you can access it. You can use it as much as you want to show the power of the Unistellar network.
Do we have any other questions? Let's see. Let's go to start.
Any other questions? That is a start. Okay.
All right.
So I have a question for you.
Oh, okay. What's your question?
So what will be for you the next big thing we should do in the exoplanet field of research in citizen science?
Oh, I have my dream.
Okay.
And we've been going after it, so I feel like a broken record.
Go ahead.
But I would love so much if this year we could help determine the period of a test duo and break the degeneracy. So essentially degeneracy in science, which is where there are multiple parameters that would fit and you don't know which one it is, essentially, like in a very basic way. And for some test exoplanet candidates where only 2 transits have been detected, there's this degeneracy with the period. We think there's a planet, but we don't know what the period is. And I would love more than anything for us to take one of those candidates and break that degeneracy and be the ones to actually find out what the period of that planet is. And we've been doing work on that.
Oh.
It takes a while because it takes a lot of observations over a long period of time.
Okay, we have a question from Nico Adams, who wants to know about the scientific questions in the asteroid occultation program. Well, that could be a lecture. So you ready? I think we have a half hour, right?
No, we got about 30 seconds.
Okay. There is multiple of them. If you have an asteroid for which you know well the position, like for instance, in a main belt, what you're looking for is to know the size and the shape, and also find out if there is a companion around them.
Like the binary.
The binary, for instance, or rings. We also have rings. Okay. If the reason we want to do that is because this allows us to characterize better these asteroids and have a better idea of, for instance, if there is knowing the frequency of asteroid with moon, give us some idea of the collision rate in the asteroid population. How often those things impact each other, and also their composition. Because if you see a moon, you know you will be able to know the mass of the system, and if you know the size, you derive the density. And we have seen that asteroids have a density that varies from 1 gram cc all the way to 5 and even 7 for a few of them. The 7 are metallic, basically, asteroid, and the 1 are typically carbonaceous chondrite C-type asteroids, and they have water in it as well, and a large portion of void. They are rubble pile. So we have seen this diversity, but we don't have enough data point to truly understand where it's coming from. That's one case. The second case, and I'm talking a lot about that if you look at my tweet and Blue Sky activity at the moment, is that with occultation, you can also derive precisely the position of an asteroid. So we have this asteroid called 2024 YR4, and that's a beautiful name, that has a 1% chance of impacting our planet in 2032. Everybody's talking about that at the moment. I don't know if it's still the case, but it would be super interesting to be able to observe an occultation of this asteroid, for instance, because we will know precisely the location. Because we know very well the location of stars, thanks to a mission called Gaia. So we know the position of the asteroid. So we'll be able to know whether or not this asteroid will impact our planet very quickly. So those are some of the main scientific questions. There is also the presence of rings on asteroid, which is still unexplained, be detected by computations, etc., etc. As I say, I can give a long lecture about that. So let's take the other questions. I think there's a question from Astro. Oh my God. Seriously, guys, are you, Astro, are you in the office? Because I just talked about that yesterday. Yesterday, on Tuesday, I was meeting with Ryan, Ariel, and Joseph, and we talk about exactly that. Will it be possible to characterize artificial satellites using occultations, so using our telescopes? So we are going to have a satellite program pretty soon, with the goal of refining orbits of satellites, mostly. But I'm now also considering having a program in the future to do occultations of artificial satellites, so we can get their size more precise. This is super challenging. We're talking about like very short occultation, so it's
and very dim objects in some cases.
Yeah. So we will have this in the future.
We can talk more next time, like they suggested. Yeah. Absolutely.
Okay. Good. Well, that's all for me.
Yeah.
Anything else?
Thanks, everybody. Just keep watching for what's going to go on in 2025 on our science.unistellar.com website. In the next day or so, we'll be essentially posting some really exciting things to do in these next couple months as we get a start to 2025. That Uptempo exoplanet campaign, as well as another occultation that's coming up as well. So keep an eye out. Great job in 2024, and we'll see you next time.
Bye-bye. Take care.
Bye, everyone. From Italy, from California, from Ireland, all around the world.